In example one, we're given a graph and we want to evaluate some of the information below. So let's take a look at those limits and then also some function evaluation here. And we're going to see if we can figure out what these are equal to. So let's take a look at part A here. It says h of -4, and notice the lack of any limit notation here. So this is just function evaluation. So let's go over to the graph here. We've got -4, and then the question is, what is the y value here? Now, even though the point -4, 2, or the coordinates, I should say, -4, 2 are listed, that gives us coordinates of a whole. When we draw an open circle, we're indicating that that function actually does not have a point there. So we're going to say that h at -4 is undefined. There is no corresponding y value for an x value of -4. If we look at part B, C, and D, the notation is a little bit different. Here, and here's how we're going to read this, for part B, we have the limit as x approaches -4. And then there's this little sign up here. I don't know if you can see that there, but it's a negative sign. That's in the exponent position. As an exponent, a negative sign just wouldn't mean very much. And instead, this is limit notation. And so that little negative sign means from the left side only. If we look at the following example, part C, we see the plus sign right here. That plus sign means from the right side only. Right there. So we would read the first part of this, the limit as x approaches, that's what the little arrow means, approaches -4 from the right side only. Let's take a look at part D. Notice you don't see any symbol up here. So this is called a two-sided limit, or the function has to approach the same value from both sides. So let's work through B, C, and D then. We'll see if we can figure out what this is equal to. So let's do B. B says from the left side only, and we're still approaching an x value of -4. And the key here is that we need to be at a point that's on the function. So as we get closer and closer and closer to -4, the question is what y value am I approaching or getting close to? So it looks like when x is over here, -5.5, our y value is 0. Then when x is 5, our y value might be, I don't know, a little less than 1 there. When x is equal to -4, so we'll do that next here, -4, let's do -4.5, so that would be like right here, and then the y value is about 1.5 or so. And so what's happening to the y value as we approach -4? Well, the y value was 0, then it was 1, then it was 1.5, and as we get even closer to the x value of -4, it looks like our y values are approaching or getting close to 2. And if you thought 2 for this one, you're on the right track. So it's kind of weird, even though that the function doesn't exist when x is exactly equal to -4. For a limit, we're not concerned with that. We're just concerned with the value that the function is approaching or getting close to. Let's take a look at part C then, and the answer to that one, by the way, was 2. So part C, as we approach -4 from the right side only, remember we're getting close to, but not exactly equal to -4. And we're wondering again, what is that y value that we're approaching? Well, here the point has a y value of 4, and here it might be 3.5, and here it's maybe 3, and then 2.5 for the y value, and then 2.1 right here, and 2.01 right here. And so we can tell here visually that the function is approaching or getting close to a value of 2. So we would say the limit as x approaches -4 from the right of h of x is 2. What about this two-sided limit over here for part D? And the key here is that we need to have the same value we're approaching from the left and the right. So from the left, we're approaching 2. From the right, we're approaching 2. And that missing number there is, well, 2. And so we would say that the limit as x approaches -4 of h of x is also 2. So that's a key here. As long as the limit as x approaches -4 from the left, that's this guy, and the limit as x approaches -4 from the right, that's this one, if those are the same, then the two-sided limit will exist. And that both of those have to approach the same value. All right, let's try a different row here, and we'll be looking at a different x value. So here we're looking at x is 1, and then let's go ahead and run through E, F, G, and H. So the first one, there's no limit notation. So you don't see any limit notation right here. This is just function evaluation. So we're going to go to 1, and then we're going to go up or down until we find a point. Now, keep in mind this point doesn't exist here. 1, -2 is just locating that hole. So if we go vertically up, we would see this point does exist, and the output happens to be 4. So h at 1 for this particular function is 4. Nothing new there. That's just function evaluation. F, G, and H are different. So let's try F. That's the limit as x approaches 1 from the left. So I'll approach 1 from the left. And as I approach 1 from the left, my y value approaches or gets close to 4. And that's the kind of language we want to use for limits. For part G, we're approaching 1 from the right. So now I'm coming from the right or larger values than 1, and I'm approaching or getting close to 1. And I can see that the y value, as I get closer and closer and closer to an x value of 1, that y value gets closer and closer and closer or approaches -2. For the two-sided limit to exist, the limit from the left has to be the same as the limit from the right. Here we can see here that the top red arrow approaches 4 from the left. From the right, the bottom arrow approaches -2. We've also listed that as our answers for part F and G. Because those are different, this limit, we would say, does not exist. And you can abbreviate that by simply writing, and we'll do this in the future, DNE. And we use that kind of language for limits, saying that they don't exist. And in this case, the two-sided limit here doesn't exist because the limit from the left is not the same as the limit from the right. Okay, let's work with the last row here. We're going to be working with, it looks like when x is 6. So let's see if we can figure out what's going on there. So let's see here. When x is exactly equal to 6, I'm going to go up or down until I hit a point that's on the graph, and it happens to be this one right here at 6, 2. So h of 6 is 2. Now you might say, well, gosh, that's got to be the limit, but we found out before in part A that the function was undefined, but the limit still existed. In part E, the function was defined, but the two-sided limit didn't exist. And then in I, we have the function existing at 2, but we need to be very careful in investigating J, K, and L. And we're going to investigate what happens as x approaches 6 from the left here. So we're going to be any number for x that's less than 6. So we're going to try to get closer and closer and closer to an x value of 6. And as we get closer to an x value of 6, we get closer and closer to an x value of 5. Let's think about k now. That's x approaches 6 from the right. So I'm going to be any point on the function to the right of 6, and then I'm going to try to approach or get close to that x value of 6. And we can see here that my y value is approaching 5 right there where that missing point is. Remember, it's not exactly what we're equal to for limits. Now that we figured out that the limit from the left is the same as the limit from the right when x approaches 6, we can actually say that the limit as x approaches 6 is also 5. This is kind of confusing to some students. They look at it and go, well, why is that different than what the function actually exists at? And this is a key thing to highlight for a limit. For a limit, we are not caring at all exactly what's happening when x is 6. For function evaluation, we do. And so it is possible for the function to exist at a different y value than what the limit would exist at. And you're going to find that when there's this thing right here called a hole or point discontinuity. Some people also call that a removable discontinuity.